how did I measurement on two as the red forces? Take a look. Basically, these are the main topics in these three chapters, 21, 22, 23. One first concept is force acting on moving charge. If you have magnetic field, most of it is about magnetic forces. If you have charge moving charge Q, moving with velocity v in magnetic field. So there is magnetic field at any arbitrary orientation. This is a uniform magnetic field. Uniform means direction and magnetic is the same. And there is a certain angle between V and V. What is magnetic force acting on this charge? When you look at this graph, you see certain things. You see Q, you see P, you see B, then you see theta. And magnetic force is basically the product of all these things together. Magnetic force is Q times B times B times sine of this angle. Okay, this is basically the formula. This is also the concept. We are using this concept to solve simple problems. For example, if you have a Earth has magnetic field. Suppose this is the north, and this is east, and this is west, and this is south. Suppose it says the Earth magnetic field is to the north, but down below the horizontal by 25 degrees. This is B vector. To the north, but not horizontally, but below. And you have a charge moving to south direction. Okay, this is positive charge, which is moving to the south. Find the magnetic force acting on this charge. The charge is given. Magnetic field magnitude is given. Velocity is given. Determine magnetic force. So this is basically your B vector, and this is B vector. Find this angle. This is 180 degrees minus 25 degrees. This angle. Okay, this is the angle between V and B. Or if your charge is moving to the west, in that case the angle changes. The angle is different. So what would be the angle if magnetic field is to the north but below the horizontal, and your charge is moving to the west? So this is north, south, and this is east-west. So your velocity is to the east, and your magnetic field vector is in this plane, but below. So what is the angle? The angle is 90 degrees. But this is velocity vector. Velocity is perpendicular to this plane and perpendicular to any line on this plane. So be careful. So sometimes you are dealing with a geometry problem. You should be able to deal with three-dimensional geometry and figure out this kind of things. So now the same thing, but when charge enters a pre-existing magnetic field. So this is magnetic field. It's perpendicular to the plane of the ball, and this axis indicates that it is going away perpendicular. Now consider a positive charge. This positive charge which enters this field with certain velocity v, this positive charge. And also there is a direction. Magnetic force is perpendicular to B and C. All these things are vectors, so they have direction. The force is perpendicular to V and to B. Now this situation, positive charge enters pre-existing magnetic field. So use your right hand rule is applicable to positive charge. This is positive charge, and you determine the direction of force. You know the force would be perpendicular to V, it's perpendicular to B, so it's likely to be on this plane, but you don't know it's up or down. So you can determine that by using right hand rule. Right hand rule, your fingers go along a V, so this is V, my fingers go along V, and V is away from you, so the force would be upward. So the magnetic force would be upward. But what happens after some time? This initially it goes horizontally, you are pushing it up. Magnetic force is pushing it up. It would go this way, right? It would go a little up. And here, when you determine this is V, but force should be perpendicular to V all the time. Now force is this direction. So it turns out this positive charge would move in a circle counterclockwise. Counterclockwise. Now what basically, this is circular motion, okay? A circular motion which has centripetal acceleration and centripetal force. Although the speed is the same, but velocity is not the same. Velocity changes direction. So basically, the whole reason of this is magnetic force. Magnetic force is a centripetal force in this case. So this magnetic force, which is QV times B, in this case, the angle between V and B is 90 degrees, so sine theta is 1, it goes away. This becomes the centripetal force, which is mv squared divided by r. This is centripetal force that we know from physics 1, and the radius of this circle is derived from here. This becomes with this speed, and the radius is mv divided by q times b. This is the radius. So now what would happen if you had a negative charge? The same situation, but negative charge. So this is a negative charge, enters this field with the same velocity. The magnitude of the charge is the same, velocity is the same, magnetic field is the same. What would happen? Now, to determine the direction of force on a negative charge, you use your right hand rule, but right hand rule is applicable to positive charge. Suppose this is positive charge. What is the force on a positive charge? It's up. We determine it's up, but because it's negative charge, the force will be down. Now this negative charge would move in a circle, but clockwise. Okay, clockwise. The force is down, it would move down, and this is the resulting in a circle clockwise. You should be able to determine the direction. Also, from here, you see that the radius is proportional to the mass. For example, if this was a proton and this was an electron, not only the charge is a different sign, but the masses are very different. The masses are different, so electron has much less mass. Less mass, less radius, provided the velocity is the same magnetic field. So if I'm asking you, would this be a reasonable drawing for a proton and electron which enter the same magnetic field with the same speed? In terms of the direction of motion, it makes sense. But in terms of the radius, these two radii are the same. No, in the sense that the radius is not reasonable. Because for an electron, you would have, if this is the proton, for an electron, you have a negatively small circle. The radius would be smaller, much smaller than for a proton. So pay attention and make sure that you can make a good judgment about the direction clockwise or counterclockwise, and also if one has larger radius than the other, then which particle is that? Is the larger radius a proton or an electron? And plus the direction of the circular motion, clockwise or counterclockwise. Okay, the next part is force outlet on current. If you have a wire with a length L, which has current I, and this wire is in a magnetic field, again, magnetic field can have arbitrary orientation. Now you have a current. You know, the current, the length of the wire is L, it's in the magnetic field B, and the angle between the current, if it's a straight wire, the angle between wire and the magnetic field is theta. So it's very similar expression for the force, magnetic force. This force acted by the field on this current is ILB, and again, sine of this angle, sine of the angle between magnetic field and the current. So, as in the case of charge, if the charge is moving along p vector or exactly the opposite direction, then the force is zero. The same here. If the current goes along p vector, they are parallel or anti-parallel, then the force is zero. So, and also, you know that the wire which has current in it, it creates magnetic field around it. And magnetic field created by long wire which has current, magnetic field is given by this formula, mu0 times the current divided by 2 pi r, where r is the distance from this wire. Okay, if you consider the magnetic field at this point, then simply make a perpendicular line to the wire, and this is R. The magnetic field is directly proportional to current, inversely proportional to distance from the current. Now, if you have two wires which have current I1 and I2 to the same direction, so what would be the force of interaction between these two wires? Two wires parallel to each other, current goes the same way, the same direction. First of all, we have determined that this force is attractive force. The force is attractive. And basically this wire exerts force on this wire, which is determined by this formula. But the magnetic field is the magnetic field created by the other wire. Okay? And basically when you replace B by this expression, you get the force expressed in terms of two currents. And this is the expression for the force between two current carrying wires. Here, R is the distance between the wires. Okay. Force acting on this wire is magnetic field created by this wire here. Okay, multiplied by its current, multiplied by the sine theta is 1 here. It goes away. So, for example, if you have force between current the same direction attractive, and if you have another current which goes to the left, force between this and this would be repulsive. So this is repulsive. So for example, if you have a wire which has current I1, And then next to it we have a rectangle which has current I2. This is circuit. If you have I2 here, it goes up, it should go this way, it is basically going clockwise. Here you have the same I2, but at a different direction. So if these three currents are given, and these two distances are given, this is A and this is B. This horizontal distance to the first left-hand side is A, and the width of this circuit is B. Find the total force between this long wire and this rectangular circuit. So you should find the force between I1 and I2, and you know that this force is attractive. This force is to the left. Okay, the force between I1 and I2 is attractive. So because of that force, this rectangle is attractive to the wire. And the other force is force between I1 and I2. Again, the current is the same, but first of all, it's a repulsive force. It's this direction. And this is F1. So this is F2, which has the opposite direction. One force on this side to the left, other force on this side to the right. So the total force would be, if you consider this positive direction, you can say it's F2 minus F1. Here, for distance, we use simply A, and in the second case, for distance, we use A plus B. And in both cases, use this same formula. And L would be this is L. Okay. Use this formula to calculate this force and the other force. They have opposite sign. The difference between two forces would be the total force between the wire and the rectangular circle. Okay, now a torque. You have a closed path of current, simply circuit of arbitrary shape. It's a plane. It's a plane, a wire, a circuit with a wire, and there is magnetic field. The angle between magnetic field and the normal to the surface is theta. So this magnetic field is exerting torque. The torque can rotate this circuit, and the torque is given by this formula. It's proportional. There is current in this circuit. Current is I. It can go clockwise or counterclockwise. And the area of this circuit is A. Magnetic field is B. And here we have again sine theta. If you have a solenoid which is more than one turn, a loop which has n turns, then simply you multiply this by n. And also for any circuit, the product of current in this circuit multiplied by this area is magnetic moment of this loop. So mu is the current times cross-sectional area. For example, if you have a number of circuits of different shapes, suppose one is a circle which has radius r, one is a triangle, equilateral triangle which has side of 2R, and in both cases you have the same current. Here you have I, here you have I, the same current, and they are in the same magnetic field. You can have more than two, like 3 different circuits. Now, in this is case A, this is case B. So in which case the torque is larger? Tau A is more than tau B, or the opposite. So determine this. Basically, from here, you know that because the orientation is the same, magnetic field is the same, N is 1, the whole thing is determined by the product of current and area. But in this case, the current is the same. Even the current is the same, so the whole thing is determined by the area. So simply determine the area of this circle and the area of this triangle and compare. Whichever has larger area will experience larger torque. But be careful, because the current also may be different. If this has a smaller area but much larger current, then the torque may be larger. Just calculate the current times area and determine in which case you have larger torque. So you should know simple geometry. You should be able to calculate the area of a triangle and the area of a circle. Some people tell me that the area of a circle is 2 pi r or something like that. So make sure that you have read those appendices at the end of the book. There's one and a half page which gives these basic formulas for geometry. Okay, now Faraday's law. This is about induced electromotive force and induced current. So, if you have a circuit which is in a magnetic field, then there is a magnetic flux across this circuit. Once this magnetic flux is changing with time, so you are creating current in this circuit. Okay, any circuit of arbitrary shape, again, there is perpendicular to this surface, and there is magnetic field. This is B, and this angle is theta. So there is magnetic flux across this circuit. This magnetic flux is simply magnetic field times area times cosine of this angle theta. Faraday's law says that once magnetic flux is changing, you create current. Okay? And in order to have current, you need some voltage. And this voltage is called induced voltage or induced electromotive force. Electromotive. You can move charge, move electrons. Electromotive force is, if you have more than one term, they multiply by the number. If for simple wire, N is 1. It's the magnitude of this voltage, this change of flux with time. Okay, this is it. But when you look at this, you can say that the flux can change because of changing magnetic field, changing area, or changing orientation. And we can have several situations. For example, you have a circular circuit. It has a certain resistance. Okay, a certain resistance. This resistance is R. The radius is circle. The radius is R. This whole thing is in a magnetic field, and magnetic field is changing. You are given the radius of the circle the resistance of that circle angle theta here between magnetic field and normal to the surface. And magnetic field is changing. Initially, magnetic field, let me call it B0, is 3.4 Tesla. And after 5 seconds, let me call it B, 5 seconds is 2.9 Tesla. Magnetic field is changing, therefore flux is changing. Magnetic flux is changing. You should find the current. You should find the current because of the changing magnetic field. Okay, current in a circuit is ohmic resistance. The current is voltage divided by resistance. Okay, it's a voltage. I simply call it voltage, which is the same as electromotive force. This electromotive force is voltage, which creates current divided by R. Here, I know the resistance, but I don't know the voltage. And voltage is given by this formula. Okay, by this formula. The voltage is the change of flux with time. Does the area change? No, the area does not change. So it stays constant. What is the area of this circle? Pi r squared. Okay, and I write this cosine theta. It is not changing. What is changing here? Magnetic field is changing. So delta, here I have delta D over delta T. Change of field with time. Change of field with time is final magnetic field minus initial. 2.9 Tesla minus 3.4 Tesla. This is delta D divided by delta T. Delta T is simply 5 seconds. Divided by 5 seconds. Okay, if in another case, it may say magnetic field is constant. Okay, suppose it is 3.4 all the time. Magnetic field is 3.4 Tesla all the time, but the angle is changing. This loop is turning. Suppose initially it is constant, and theta initially is 60 degrees, and theta after 5 milliseconds, 5 milliseconds is 20 degrees. In 5 milliseconds it changes by 40 degrees. What would be, again, the current? Current is given by this. I need to find the voltage. In this case, I do this here. Again, area is not changing. Magnetic field is not changing. This multiplied by B, which is this. And now delta cosine theta. Final value minus initial value. Cosine 20 minus cosine 60 divided by delta cosine divided by delta t. Delta t is 5 milliseconds. 5 times 10 to negative 3 seconds. Okay? Here the angle is changing. In a previous case, the magnetic field was changing. In both cases, the flux is changing and you have induced current. And you can determine the current by using this formula and this formula. When you have sinusoidally changing something like current or voltage, make sure that you know what the root mean squared is. Every value, root mean squared. If you have a current is changing like this, so this is amplitude, maximum value. So RMS value, root mean squared, is the maximum value for the amplitude divided by square root of 2. So make sure that you know this. Okay, it's very simple. If you have an inductor, in a circuit and you are changing the current from 0 to a certain value of current, then during this increase of current, you are pumping energy in this inductor, and this energy is given by this formula. 1/2 inductance times the square of that current. So here the important thing is energy is proportional to the square of current. If you change current n times, if current increases n times, then U increases n squared times. If you increase it 2 times, you are pumping 4 times more energy, and so on. So there may be some multiple choice questions. You should know this principle to answer the question. So motional electromotive force, if you move a conductor in a magnetic field, you can create voltage. Voltage or electromotive force, in this case we call it motional because it's created by motion. You are moving, suppose you have a circuit which here we have a bulb, and you have the resistance of this bulb, and you are using a bar of a conductor, and there is magnetic field, again going away perpendicular to the plane of the picture. So if you are moving this bar of conductor with certain velocity v to the right or to the left, you are creating voltage. You are making this a battery. It creates voltage, and this voltage can be used in this circuit. So there is contact here. It can slide on this U-shaped wire with electric contact between them. So total voltage created is, suppose this bar also has some resistance itself. Suppose this resistance is lowercase r. The resistance of external circuit is a capital R. So the induced electromotive force is, and the length of this bar is L. Okay? Now suppose this is the total voltage. Suppose these two resistances are given, external and internal resistances are given, the length is given, magnetic field is given, and you know that you are moving it with certain velocity, you are creating a current. You know that current, but you don't know at what velocity you should move it. Okay, if you move too fast, you can create too much current and your bulb can burn out. If you move it too slow, you may not have any light in the bulb. You should determine at what speed you should move this bar in order to get this particular current in this circuit. Okay, now again, total current is total voltage divided by total resistance, and this is total voltage. Total resistance is the sum of external and internal resistances. But total voltage, electromotive force is given by this formula. So it's V divided by R2 plus R. And from here we have one equation with one unknown. If we ignore this intermediate part, so you get this, and from here determine that V equals I times R plus R divided by V times Z. So these are very simple problems. So especially when you have your formula sheet, basically your job is to identify which formula to use. Okay, now consider this is combination of Faraday's law and Lenz's law. Again, when magnetic flux is changing in a circuit, you create current. Suppose here again you have a magnetic field, and the circuit is entering this magnetic field. But we have different shapes of circuit. Suppose case A, you have a square wire conductor. Each side is 2L. In case B, you have a rectangular wire which has L here and the 2L here. In all cases, this thing is at the edge of this magnetic field. Only in this case there is magnetic field. Outside of this case there is no magnetic field. Basically this circuit is entering. It's about to enter this magnetic field. And case C, you have a smaller circuit with the sides L and L here. So this magnetic field is B. And the question is, in which case of these three, in which of these three cases, when you start entering the field, then the whole thing is already in the field. You start here, and when this whole thing is already in the field, something is changing, and you are creating induced electromotive force. In which of these three cases you get larger electromotive force? Case A, case B, and case C. In all cases, you have the same velocity. Velocity is to the right. All these three things are entering the field. When this whole thing enters the field, it creates something is changing. Certainly, you create electromotive force. And you should determine, for example, electromotive force in A is larger than B, is larger than C, or some other combination. So electromotive force is determined by Faraday's law. It's delta phi divided by delta t. Right? Now, what is changing here? And phi is b times a. So b is constant. What is changing? The area. Change of area exposed to the magnetic field is changing when this circuit is entering the field. When it is totally within the field, it's not changing. The whole area is in the same magnetic field. But when you move this thing to the right, more and more area is being covered. So basically the magnetic flux across this whole circuit is changing. Initially it is zero. When it's totally in the field, it is maximum. Basically, the area is changing, and therefore you can write this in this form. This equals B is constant, the area is changing with delta T. So now compare these three cases. Case A, okay, epsilon A equals B times, what is basically the change of area is the total area. Initially, the area covered with the field is zero. When it is totally in the field, the total area is in the field. So basically this delta A is the total area. You have 2L times 2L, 4L squared. Delta A is 4L squared, 4L squared. Now delta T. So what is the time required for this square to enter totally the field? Time. So this is the distance traveled, 2L. It travels this distance in order to enter the field, right? Time is distance divided by velocity. Basically here we have 2L divided by V. Okay, then you can simplify this 2 4L squared. This cancels away. Here we have 2, 4 divided by 2 is 2. L squared divided by L is L, 2 times L multiplied by V. This V jumps in the numerator. 2 L times V. Case B, epsilon B equals the same field and multiplied by the change of area. Here again, the change of area is the total area. Initially zero area is covered with the field. Finally, the total area. The total change of area is the total area of this rectangle, 2L times L, 2L squared. 2L squared is the change of area. What is the time? The time is again distance divided by velocity. What is the distance? It needs to travel this distance, right? When it travels this distance, the whole thing is in the field. Distance traveled is L, and velocity is V. Again, you simplify this L cancels away. We have 2L times V. Now, case C. Electromotive force is V times delta H over delta T. What is the total area here? L squared. L squared. What is the time? Change of area divided by duration of time is L divided by V. Right? Distance divided by velocity. So here we have 2 times less. This I should multiply this by B. Okay. 2 times B, L times V, 2 times L times V. Here we substitute B times L times V. And my answer is this. Epsilon A equals epsilon B, which is larger than epsilon C. Okay, this is the way to solve this kind of problem. Also, I can ask you to determine the direction of current in each of these loops when they are entering the field. Determine when they enter the field, they are creating voltage. Okay, this voltage will create current. So determine the current direction of current, clockwise or counterclockwise. Now determine the direction of current when this short circuit is inside the field here. And determine the direction of current when the circuit is exiting the field. Here we are using the Lenz's law. When this circuit, any of this or this one, when they enter the field, they are increasing magnetic flux, increasing magnetic field. And this magnetic field is increasing, it is away from you. What would be the magnetic field created by this loop because of induced current? Magnetic field, when they enter the field is away and increasing. Would you create the same direction away? If it's away, no, you should create a field, magnetic field toward you. To minimize this increasing, to oppose the cause of this, because Lenz's law says induced current opposes the cause. The cause of this current is away, magnetic field increasing. Okay, you should create the magnetic field toward you, and you can create magnetic field this way if you create counterclockwise. So the current is counterclockwise when the circuit enters the field. What is the direction of current when this circuit is traveling totally inside the field? The current, induced current, is created by changing magnetic flux. Is anything changing here? Does the area change? No. Does the magnetic field change? No. Orientation? No. So there is no induced current inside. Now what is happening when you're exiting the field? Each of these loops is experiencing decreasing magnetic field away from you. It's away from you, but it's decreasing. You need to keep it from decreasing. You are basically induced current is opposing the change. It's away from you, but it's decreasing. You should keep it away So you create a magnetic field away from you, and you can do it by creating clockwise. Okay, when it's exiting, the current is clockwise. When it's entering, it's counterclockwise. Inside, there is no induced current. Okay, this is a problem which is related to magnetic force on the wire. Again, everything is related to magnetic field. Suppose in a confined part of the space, we have a constant magnetic field. B is given. Okay, and then we are creating a suspended bird perch. Okay, this is a little circuit which goes like this. Okay, it has this more or less rectangular, it has certain resistance in it, it has voltage. Voltage, suppose is a 9-volt battery. And then you are making a bird perch. This is something that can be suspended. You want to create current in this circuit in a way that the force cannot from this circuit upward. And this should be enough force to equilibrate the weight of the whole thing, this bird perch, the bird sitting on it, and the circuit itself. Okay, now B is given, the voltage is given, the total